Okay, there are only two topics left, inverse functions and composite functions. I'm tweaking the order a little bit. Inverse functions, in my opinion, are a little bit easier than composite functions, so let's talk about inverse functions first. Let's begin with one-to-one function. What is a one-to-one function? Well, here's really formal definition. Function values are different whenever original variables are different, but this is a bit too intimidating. In reality, it's kind of like this. Any element of domain uniquely determines an element in the range. So if more than one elements of domain share a same value in range, then it is not invertible. It is not 1-to-1. It could be 2-to-1 or 3-to-1, things like that. Those are functions, but it is impossible to define inverse function. For example, if two or more values share one value in the range, now how can you come back? Which one is right one? So we cannot go back, and we need one-to-one function if you really want to come back to the original place. Here's an example of a one-to-one function. Y equals to x cubed minus 1, and as you can see, given y coordinate value in the range is assigned to 1 and only one x coordinate value in the domain. Here's an example of a function that is not one-to-one. Given y coordinate value is not uniquely determined by one x coordinate value. For example, if you select y equals to 0, then excuse me, both x equals to -1 and +1 will give you y value 0. There are more values. In any case, this is an example of a function that is not one-to-one. Now, how do we check a given function is one-to-one or not from a graph? We use horizontal line test, and we have this example, 3 graphs. Which one is one-to-one function? Well, those 3 are all graphs of functions. They all pass vertical line test. Given x coordinate value, we have only one y coordinate value assigned. But can we go vice versa? Given y coordinate value, do we have only one x coordinate value assigned? We can find out through horizontal line test. And the middle function, this red graph, is okay. If I draw horizontal lines, no matter where I draw, you'll have only unique crossing, which means for that y coordinate value, we can have only one x coordinate value that will give you the point on the graph. But if you look at the blue graph, in some cases, you'll have those 3 crossing points, which means for that particular y coordinate value, we have 3 x coordinate values, or those 3 x coordinate values share the same y coordinate value as function value. The green one is even worse. Now, if we have one-to-one function, which means given y value, you have only one x coordinate value to go back, then we can define an inverse function. We start from x and then get to y equals to f of x. And then from y, we can come back to x because there's only one x value that defined y. So we can just come back to that same x value, original x value. Now, if you have more than one x coordinate values coming to the same y value, then you cannot go back to the original place. You may have to guess, and that you may not be always right. The notation for inverse function is something like this. Looks like negative first power, but it is not 1 over f. It is inverse function notation. And it's kind of like this. If y equals f of x, then you can come back to x if I start from y. So that is equivalent to x equals to f inverse of y. So x equals to f inverse of y means y equals to f of x, and vice versa. Now, it is a little bit more traditional to use x as a starting variable inside. So let's switch x and y then we have y equals to f inverse of x, and consequently that's equivalent to x equals to f of y. So basically we just switched x and y. We just switched x and y. I said it twice. That's an important observation. Whenever we have inverse function, we have to switch x and y, and then if they are equivalent, we'll have to do something like that. Well, maybe I'm not really making too much sense, so let's go over to a example here. Let's look at the graph first. Excuse me. I'm going to come back to 5.4 for domain and range, but let's look at the graph first. Visualization first. Here's a nice example. Blue is y equals to x squared, f of x equal to x squared, and then red is g of x equals to square root of x. Now everybody knows squaring and square root are inverse procedures. Take the square root of squared and we get original x back, and vice versa. A square root of x and a square it, and I'm going to get x back. So they are inverse of each other. And, oh, one more thing. The blue function, f of x equals x squared, is not one-to-one function in general, so we have to restrict my domain. When x is greater than or equal to 0, as you can see in this picture, now it passes horizontal line test. If you have the left-hand side, the negative part of this parabola, then it fails the horizontal line test. In this case, it's okay because obviously we are restricting our domain, and in this case, x squared and square root of x are inverse of each other, and we have appropriate symmetry there. A symmetry is the symmetry with respect to the diagonal line y equals to x. Now, why do we have the symmetry? Did I emphasize is inverse function is basically switching x and y, x going to y, and then y coming back to x, switching x and y back and forth, back and forth? That's exactly what it is. If I fold over y equal to x, this diagonal, which is purple dotted line, then x-axis is mapped right onto the y-axis, and vice versa. Y-axis will be mapped right onto x-axis. And if you look at the graph, the blue original graph is mapped onto the inverse function, red one g, or vice versa. We can start from g and then take the inverse function, which means take the inverse procedure, and then we're going to get blue, and that's given by folding with respect to the diagonal. The reason is because we are just switching x and y. We have another graph, another pair of graphs behaving pretty much the same way, and we have f of x equals e to the x power function. It's an exponential. G of x is logarithm of x, log of x. And what we have inverse procedure. Log and exponential are inverse of each other. And not surprisingly, we have symmetry with respect to the diagonal line y equals to x. Let me ask you again, why do we have the symmetry? That's because we are switching x and y. X goes to y and y goes to x. That's basically what inverse is doing. X-axis going to y-axis, y-axis going to x-axis, blue is going to red, red is going to blue. Alright, now we visualized the switching. X is going to y, y is going to x, and that'll help you understand this relation. Domain of f is range of inverse function, and the domain of inverse function is the range of the original. Why is that? Domain is allowed x coordinate values, and then range is allowed y coordinate value. And then if you look at inverse function, we're pretty much switching x and y, isn't it? So x here is y for inverse, so domain of f is range of inverse, and vice versa. Domain of inverse, x for inverse is y for original, so we have range. Let's verify that with these pictures again. Let me copy and then bring it down over here so that I can really see this. Excuse me. Domain of f in this case, look at this blue curve, then this is 0 to infinity. This domain of f, in this case, domain of f is in this case 0 to positive infinity. The right hand side, because we just restricted, otherwise we do not have one-to-one function. And that's the same as range of inverse function. And well, look at the y-coordinate values of inverse function, red one, and that goes from 0 to positive infinity. And then how about range of the original function? Look at the y-coordinate values of the blue graph, and that's the range of the original function, isn't it? And then that is also going from 0 to positive infinity. That's the same as domain of the inverse function. X-coordinate value is going from 0 to infinity if you look at the y graph. If you look at the red graph, excuse me. So those are visible there. Let's see. What if we look at another pair of graphs here? Excuse me. Oh, this cough is. I'm sorry, but this cough is really killing me. F of x is e to the x here. G of x is log, so that's g is inverse function. What is domain of f? Domain of f in this case is negative infinity to positive infinity, because if you look at the blue graph, in terms of x value, it goes on forever to the left hand side, also to the right hand side. And that is also the behavior of the red graph. In terms of y, it goes to negative infinity, it just goes down, 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 and then it goes up very slowly. Yes, I have to move very much to the right, but red graph blow up to positive infinity too. Now, how about the range of this this f? Then exponential is always positive, so we have 0 to positive infinity. That's your range of f. And how about the domain of this red function? It is defined only on the right hand side, only when x is greater than 0. So we have the same behavior. Domain of inverse function, the red function, is from 0 to infinity. And look at those algebraic expressions. Yes, we have logarithmic function. So inside of log is always strictly positive. No wonder we need 0 to positive infinity. So we looked at the symmetry behavior, symmetric with respect to the diagonal line y equals to x, and that's coming from switching x and y. X is going to y, y is going to x, and that's why we have domain of original is range of the inverse function and vice versa. Domain of inverse is range of original function. Inverse function, well, with all those fancy symbols and everything, but main idea is x is going to y and y is coming back to x and vice versa. Now, do we have enough time to do some computation? Maybe just one problem. The first problem, okay, let's do that. So y is obtained by square root of x minus 1. And how do we come back? Okay, this switching behavior. So switch x and y, and then so for y, and then that's it. Switch x and y, as we have here, we could have y equals the square root of x minus 1 switched, and then solve for y. Take the square of both sides and solve for y, and then we have an inverse function. So inverse function, f inverse, is x squared plus 1, and then the domain and range are kind of like this. Domain of f is range of inverse function. Domain of range of f is domain of the inverse function. So we have this kind of relation. And I didn't bother drawing the graph here. It's simple enough so that I think it can be left to the students. But the procedure, remember, switch x and y and then solve for y.